All right, Ray Fugit with DownStream here. We're pretty close to starting. A couple items before we do get started. First of all, this session is what's next? What's coming in CAM350 14.5 and Blueprint 6.5. Some of you, I believe, are even beta testers, so you probably have some familiarity with this. Mark Gallant will be going through this and giving you a nice overview of the new features and functionality. Our presenter here, again, Mark Gallant, is the product marketing manager here at DownStream. Has quite a few years involved in that side of things. PADS, Mentor, Raycal, Redec. You can keep throwing companies out there, but he's been with us for quite a long time now, since 2011. And he does most of our product specing and the definition whenever we do release a new product. And he's fully, of course, qualified to present what is new in this new versions of the tool. And with that, I think I'll turn it over to you, Mark.
Thank you, Ray. All right, well, welcome everyone. So this will be a presentation, a little bit, some background, and then I'll go directly into the demonstration of both CAM350 and Blueprint. So let's talk a little bit about what are the new features of 14.5 and 6.5. Our focus on this release was on the support of rigid flex and embedded parts design data. Some of this data has been around for some time in ODB and 2581, and we're finally coming around to supporting it. We have a large installed base that are doing these types of designs, and there's been a lot of requests to support it. Our secondary focus is on support of PCB cores. So if you're doing designs and you're doing some complex stack-up work, the support of cores to us means that we're going to take that core data from the 2581 and ODB. We're going to show it in the Stackup visualizer, and we're going to allow you to document it in Blueprint as a core. So we'll see that as I get towards the latter part of the presentation. I want to be clear that the data that we're taking in for this new advanced technologies is coming specifically from IPC 2581 and ODB++ imports, primarily from Cadence Allegro, Mentor Expedition, and Zukin CR 8000. So you notice PADS is not listed here. To date, PADS does not support rigid flex design in the true format. We do have some customers that are doing it. We are working with them to try to help that process, help them get through into our product. So CAM350 14.5 offers features to not only import the content, but create and modify some of the content, and of course, export. Blueprint 6.5 specifically offers custom rigid flex documentation features. So you take the data in and you need to document your rigid flex. It's a little different than the standard rigid board, and we have some new features for that. Stackup Visualizer is a common tool between the two products, and it offers updates to support rigid flex, which typically has multiple stackups, and also PCB core definition. And to go along with this new data import and remodeling of the data, we also had to enhance our 3D viewing to support rigid flex designs. It's not, when you look at the layer strata of a database that we get from, say, Allegro, you got core layers stuck in between dielectric layers. So we have to sort of bring that all together and visualize it correctly in 3D. So you probably already know this, but I just want to give a little bit of background. What is a rigid flex PCB? It's a combination of both flexible and rigid substrates. Generally, one or more flexible cores are sandwiched between rigid material. Rigid material may be used also as a stiffener. So here you see an example of two rigid boards, parts of the board on the left, and they're interconnected by a core rigid flex. What is an embedded component? So part of this update is we now respect embedded components. It's any component not mounted on an outer layer. So an outer layer in a standard rigid board, we all know that to be top and bottom. But when it gets into rigid flex, outer layers could be the outer layers for that stack-up zone. It may only be 2 layers that represent the flex core. Those are outer layers. So any component mounted on an outer layer, it could be a screened component on an embedded inner layer, or components even resting in a cavity. So what is the data that we're taking in? Again, as I mentioned, this data has been around for a while. So there are new layer types to us, our tools. And these are rigid flex specific layer types like coverlay, adhesive, and you'll see some of those in the next slide. There are also areas that we take in. Some of these CAD tools that we're working with will have areas that are very specific, a stack-up zone area, a bend area, a flex area, and those areas will be imported and respected and understood. We also have the concept of a layer profile now. So we've always had a board outline, which was the extent of the rigid board. But when it comes to rigid flex, every layer could have its own unique shape, including dielectrics. So every layer has its own unique profile. Cavities. Cavities are part of a cutout in a board. Typically, the cavity is on a dielectric layer. So we will infer the cavities by taking these cutouts in these layer profiles and produce and visualize them as cavities. One of the things you get with rigid flex designs is you get multiple layer stack-ups. For each region of the design, there's a unique collection of layers or a layer stack-up. That's a rigid section, maybe a flex section, yet another rigid section on the right. We also will get some NC punch data. Some of these flexible layers are not drilled, they're punched. And again, embedded data are parts mounted on inner layers. So we now respect and understand that a part may be on an inner layer. So when you look at the new releases, you're going to see new layer types present. And here's the list of layer types that'll be new. So we have new dielectric prepreg cores to support core definition. It used to be just standard dielectric. Now we have prepreg and core. Some of these other layer types that you see here are some of the more advanced materials that you might be using, cover coating, conductive paste, and so forth. And then, of course, embedded resistors and capacitor layers that might come in from those CAD systems. On the right, you see most of the ones we'll be dealing with the rigid flex world, NC punch route, which is an NC layer, cover lays, flex, bend, and rigid areas, also a stiffener area, and adhesive. So all of these layer types have been added to various UI components of both CAM350 and Blueprint. So a little bit more in detail about what some of these areas are. And this is more specific towards the CAM350 side. So what is a flex area? An area of the design that contains only flexible materials. So coming in from Expedition, we get an ODB file and it's going to define a flex area. So that's just a polygon. It becomes a filled shape on a flex area layer. And it's also duplicated as an area shape, similar to a rule area. CAM350's had rule areas for quite some time. And you can see that the areas pane of CAM350 has been updated to support these new areas. Bend area, much like a flex area, except it's the specific area of those flex layers where the layers are bent. And again, it comes in as a filled shape on its bend area layer and duplicated as an area shape. Rigid area, as you might expect, same as a flex area. This is where the rigid materials are. Again, it comes in as a filled polygon and a rule area. Now, stack-up zones are a little unique. Stack-up zones are an area of design where a specific stack-up combination of layers is present. So only in this area are there rigid flex layers. Only in this area are there flex layers. Only in this area is another rigid flex combination. So stack-up zones are typically defined at the CAD system, and we'll take them directly in through our tool imports. And layer profiles, as I mentioned, it's a profile of a copper, dielectric, or any other layer in the design. It's imported as an area shape. And it's going to be shown on relative stack-up layers, similar to a board outline. So I'll have one board outline still, which is sort of the extent of the design, but each layer will have its own unique layer profile. Here's just an example. Here's a design that I'll be demonstrating with today on the right here. And here's an example. Here are some of the areas you might see in this design. There's rigid areas in blue, flex areas in pink, bend areas in light pink, and stiffener area in red. Okay. So that's an example of the areas that we'll import into our tools from these ODB and 2581 formats. A little bit about stack-up zones. So in this particular design, it's an 8-layer design. In one part of the design, all 8 layers are present. One part, there's only 6, and of course, in a couple areas, there's only 2. So each of these stack-ups are only present in a certain area or zone of the design. So in this case, all 8 layers are present here. The flex layers are present here, just the 2 center core layers. There's other rigid flex stack up here, and another different rigid flex stack up here. So that's what the concept of a stack up zone. Now, layer profiles. So layer profiles, as I said, are unique shapes per layer. So in this particular design, it's a flexible core center. So layers 3 and 4, which are actually in this design, it's 8 layers, but the center layers are a flex core. So they have the same shape. And as you could see, some of the outer layers and layers between them have unique shapes. And that's what represents the layer profile. What's a part on any layer? Well, again, a part on any layer other than top or bottom layer. Parts can be mounted on either side of a layer. So you have to think about that for a minute. If I have a design, like I mentioned before, a 6-layer design, and my core, 2 layers, I can mount a part on the top of that core or the bottom of that core. That's the side it's inserted from. So we now have new designations in the data tables for parts, for not only is it what side it's mounted on as well. Now, parts can be inserted, right, mechanically or hand inserted into the design. They could be formed, screened using conductive inks, or they can be embedded, a mechanically or hand inserted part sitting in a cavity. So all of this data is present in the formats that we import, ODB 2581. We're now going to respect them and create the proper data formats in our own tools. So without any further ado, I'm going to just jump right into a demonstration of CAM350. So here's this design that I was showing a moment ago on the slides. This is a rigid flex design, 8-layer design. So when we took the data in from, in this case, it was ODB++. When we took the data in, you notice that there's a bunch of collection of layers that you may not have seen in CAM350 before, such as cover layers. Right? Now I have multiple solder mask layers in this design because there's a solder mask for the top of this stack up, solder mask for this stack up, solder mask for this stack up. So it's not unusual in rigid flex designs to have multiple solder mask tops, multiple silkscreen tops. But here you can see some of the unique layer types that are in the layer list that we've added, prepregs, cores, and so forth. Okay. Now, if I look at the layers pane as well, you'll see them here as well. All the layers. Now, these are the order in which they came in through the ODB. But in order to sort of bring the stack ups together and bring layers together as stack ups, we do that in the stack up visualizer. So I'll show you that in a second. I just want to also point out that we did make a change to support the visualization of layer profiles. We did make a change so you can actually turn on, turn off, and set a color for the board outline because you want that to be unique and be able to segregate it from layer profiles. To see layer profiles, there's a couple of options there. If you go to the color matrix and set it to design mode, and I'll just expand it here, you can see the layer profiles over on the right. And I could turn layer profiles on and off for specific layers. I'll show you that a little bit later. So here's the areas pane where we made a lot of changes to support all of these new areas that are coming in. So I'll show stack up zones. Now I'm just going to go back here to show signal layer 1 just to kind of clear up the presentation of the design. And I'll go in and I'll select stack up zone here. And you can see it shows me all stack up zones. I'm just going to right click and hide them all and say, let's look at just the stack up zone for rigid C-2. So this is a stack up zone where the stack up rigid C is present. It's also present here, right? So these two areas share the same stack up. Now, if I turn these two off and I look at rigid B, there's a portion of the design where those two share the same stack up. And so forth. Here's all the flex stack ups. So those are the zones. In that area, that stack up is present. We have other areas such as bend areas. Now, each type of area has its unique properties. In the case of a bend area, this data, again, as received through the ODB import, would have extents of the shape. What side is it bent, top or bottom? What's the bend radius? What's the bend angle? And what stack-up zone is actually applied to this bend area or present? And the purpose of that is, in this stack-up, there are these layers. So this bend area bends those layers. And here you can see flex areas. It's the only property really is what flex stack-up zone is it applicable to. Sorry, rigid areas, stiffener areas. In this particular design, it does not have any stiffeners. And here's layer profiles. So what I'll do once again is hide all. So here we can see this is the layer profile. This is the extent of the top layer now. It's not the board outline anymore. It's the extents of the top layer. This is the extents of the dielectric between PCB layer 1 and PCB layer 2, and so forth. So these are all unique profiles for each layer. And it's necessary for documentation. It's necessary for DFM to understand where that extent is. And that's where the lower layer profiles come in. I'm going to show all the layer profiles. So now I'll move on to Stackup Visualize. So we read this design in. And as you can see, Stackup Visualize has changed quite a bit here. I'm just going to shrink a few columns. So that you should notice some number of new commands here, tabs down here, and some more details in here. So the first thing is that this design has four stackups: flex, rigid A, rigid B, rigid C. Each of them are a subset of the all layers stackup, which are all stackup layers, right? You wouldn't see a documentation layer in here. You only see the layers involved with stackups. And here you can see all the layer types that came in from the import. Now, a couple of things real quick about material name. So some of you may have used Stackup Visualize, some may have not. But the material name is derived on import. It takes some details from each layer. In the case of a copper layer, it says, oh, this is a copper layer. It's 0.01 ounces thick, and it has a dielectric constant of 1. And it creates a generic name so that it can give it a material name to use with the materials table. It also picks out the material type. Well, this is a conductor layer, this is a dielectric prepreg layer, and so forth. Now, our tools are beholden to the import file. So if the import file has this data present, our tools will recognize it and assign proper layers. But if it doesn't, well, that's what Stackup Visualize is for. It's here to let you create your stackups when the data is missing. You know, the ODB 2581 didn't come out of the tool correctly, or maybe you didn't take the time to define it in the tool, so it just didn't pass. Now on the right, you can see the visualization of the Stackups. If I select the flex Stackup, there are the flex layers involved. Now, because it's a flex layer, you have a top cover layer, a bottom cover layer, and here you have a flex core, right? Double-sided flex core. Rigid A. Now here's a number of different layers involved in rigid A, the multiple cores. There's rigid B, rigid C. Now, if I want to, I can go to the multiple tab here and say, you know, I want to see all these layers Stackups together. And I click OK. Now, it just shows them left to right, which may not be a proper representation of the design. That's okay. I'll go up here and I'll put my cursor right on the title of the Stackup, and I just drag it. And now I can see, okay, yeah, that's more closely representative of what it might look like. So I have the ability to present this graphic or customize this graphic to my needs. Now I'll talk a little bit more. I'll show a little bit more of this in Blueprint, obviously, when we start talking about Stackup graphics in Blueprint. I think you'll see a lot of ways you can customize this presentation. You also have this ability to show the Stackup in 3D. As you can see here. Now I'm going to go back to the Flex Stackup and back to the All Layer Stackup, and you can see the vias present here as well. So Stackup Visualizer, I'm not going to go into depth on that. By the way, you can always zoom and scroll the mouse wheel. A lot of persons using Stackup Visual may not realize that that feature is present. Let's talk a little bit about the updates to the materials table, and then I'll go into cores in a second. So right here, you'll notice that a lot of these material names are bolded. And the reason for that bolding is because these material names don't match the material names in my material table. So I can go look at my material table and I can see that, yeah, it's a very minimal list. This is actually our default list of materials. So how do I get these new materials into the table? That's fine. Easy. I just go here, save new materials to material table. So now they went from bolded to non-bolded because now they're all present in the table, right? So now you're saying, Mark, why are those bolded? Well, so bear in mind that there are 3 stores of material tables in CAM350. There's the store of materials table in the design. There's the store of the materials table on the local PC, and the store of the materials table on your master materials table, just like a CAD library, a footprint library that you might have somewhere out on a server somewhere. And that's where this mismatch is coming in. It's saying, yeah, okay, the design has been updated, but there's these materials in bold don't exist in your master or shared materials table. Do you want to update that? Now, I just happen to have a local shared table for demonstration purposes. But if I click on that, now all the materials I imported from the design with their names, their properties are in my materials table and in my shared materials. So everything's in sync. Now, in this particular design, I know there are several cores. So I'm going to define this before, before I go that further. Let's say I finish this Stackup. Everything looks good, but I want to reach out to my manufacturer. Hey, this is what I'm thinking of doing for this rigid flex. This is the layers I'm going to have, the materials. So I'm going to export the Stackup and give it, I'll send it to vendor. I'm going to send this Stackup to the vendor. It's an HTML file. It's really a 2581 file. He has a tool that he can read the 2581 file in, look at the Stackup layers, say, yeah, don't think that's right. And he sends me back a revised Stackup. So I'm going to go ahead and import that Stackup. And let's see what happened. So he added a prepreg here. I was missing a prepreg between the cores. He changed some material thicknesses. He decided what rigid core he was going to use here and made a few other changes. Now, unfortunately, his tool came back with new materials. So those materials aren't in my table, but that's okay. We could just update the table. Now I'm good. Another thing about his tool is he wasn't able to tell me that this is not actually a prepreg. It's a dielectric core. And just because the data wasn't in his file, I can set it here and I'll say that this is a flex core. I know that that's a flex core. Now that I've got the right details, I'm going to go ahead and assign my cores. So I select 2 layers. This is now a core. Notice the graphics change. I select these 3 layers, right? A double-sided rigid core. I make that a core. Notice what happens in the graphics. This is a flex core. Make that a core. Notice the graphics changing as I assign these cores. There's also going to be some benefits in Blueprint when you do this. I'll make this a core. And make this. So now I have all these cores. Now, because I made new core materials, right, I need to send those to the materials table. Now I look out at my materials table and all my core materials are there. So here is where you can define cores. If you're using a lot of same core materials all the time, you can define them here. I'm not going to go into depth on defining them. Just so you know, there is a tutorial with the product that'll help you go through some of these steps, pretty much following what I'm doing here. But the idea is that these materials were used, these materials from this table, I'm going to update the shared materials table, were used to create these cores. In other words, a material has to be present to be defined as a core. So on this tab of the materials table, I define cores, I delete cores, I can even copy a core. I can give a core a unique name and a unique description, maybe a manufacturer's part number. And now the cores are here, they're visualized. I can see them in CAM350 on the right. If I go to multiple now, rearrange, and I could see it's starting to look like a rigid flex stack up. I could see the cores, I could see the cover layers. I could see the solder masks up here for each of these different sections. Now, sometimes you're working with a large design and it might have a lot of cores in it. And cores, as you can see, when they're identified, there's a graphic appended to the layer name and prefix the layer name. So that you got core and the backslash. Those are just graphic pieces added in the dialogues. They don't actually change the layer name. It just gives you a visual that, hey, these are a core. Now, if you do have a lot of cores, you can choose collapse cores and it will shrink the visualization in the layer table. So, you're not scrolling constantly through all these cores and you can see what it does here. And it will actually show you the material name for the core. I didn't change it here, but that's the default material name for this core. I can expand it again. So collapse cores is just a visualization to help you see the core layers a little easier. So now if I click OK, because I've made a lot of changes in CAM350 to materials, I've assigned cores, it's going to update my layer table. I'll click OK. And you can see that in the layer display panes, I can see my cores here, right? So it properly updates everything across the board so that I know when I'm looking at a core. Now, because we did all these Stackup definitions and we did these cores, when I go to 3D, I just turned on show all layers, you could see that it properly adjusted the visualization of this so that I can see these layers properly. For instance, if I'm just rolling it here, I'm trying to just get the perfect zoom. So here you can see that this core, this section of rigid is much thicker than this one. So notice the components are properly presented on their top Stackup layer. Silkscreen too, solder mask. So we took all these layers that were random order in the in the strata of the database, using the Stackup details, we properly present them in 3D. So now you can see the flex, you can see the cores, you can see the rigid, and so forth. Without that data, without that understanding of what a rigid flex design is, these would just be disparate layers. You'd never be able to visualize this properly in 3D. So that's what, as far as I'm going to take the demonstration of CAM350, you've seen the updates. If there's time later in the presentation, there are a couple more things I want to show that are unrelated to rigid flex, which are some DFM updates. But I do want to make a point here. If I'm going to do a DFM spacing check, and I use the layer filters, right? If I set something as outer electrical, well, in the past, we've always understood that to be top, bottom. But now remember that outer electrical is now not only top and bottom layer for this stack up, but it's top and bottom for this stack up, and this stack up. So we've really taken the time to make sure that all of the intricacies of the DFM tool and their layer filtering will actually honor some of these filters. So you don't have to concern yourself, well, hey, you know, I chose outer electrical. How do I know it's going to get the outer electricals of each stack up? Well, we've taken care of that. So keep that in mind if you are doing a lot of analysis for rigid flex. Now, as Rick mentioned in the previous session, our plans to expand the DFM analysis for rigid flex over the next couple of releases. So now I'm here in Blueprint, same design, and I want to show some of the documentation features that we've added. So I add a new fabrication drawing. And what you're going to see over here in the fabrication palette is we've added several things here. The first thing I'm going to talk about is a rigid flex stack up. So I just drag it and drop it on the sheet. So what is rigid flex stack up? Maybe some of you haven't ever documented a rigid flex. What it is that you have to show all of the stack up variances in a rigid flex. Now, what I've seen is the various types of presentation that a user could make. We tried to accommodate that by putting some new features into the template. It's a very specific template features here. So when I double click here and look at the stack up, format the stack up, the first thing you're going to notice is the stack up list. This is a new tab here, specifically to this rigid flex stack up. When you read the design in, it reads the stack ups in the order in which they were imported, but that may not be the presentation that you want. But the stack up automatically assumes that you want to show all the stack ups, so it just puts them over to the right. So in this particular design, I want to move this flex stack up in between these two, and I also want to add a second presentation of the flex to the right. And I'll just do a preview here. And now I see exactly, you know, that's closer to what I want to see when I present it to the fabricator. So you have complete flexibility over each of these presentations. In fact, notice that the vias are present in each of the presentations. Well, it only puts the via spans that make sense for that section. Well, let's say I really don't want them in all of the spans, so I'm going to take them off. I don't want to show it in the flex because I really don't have any drills in the flex, and I don't have any drills in this area, so I'll preview that. And now you can see, oh, I think that was my fault. Oh, sorry. Go back. Sorry, I put it, I have to move that down. I put the rigid flex in the wrong spot. There you go. My fault. So now I can take the vias out and only show the vias in the rigid sections. Now, maybe this section's not thick enough. Maybe I have 8 via barrels here. That's okay. I could go in here and change the width of this. So what is the width value? The width value is basically 1 times the graphic width in the template. And what I mean by that is if I edit the template, this graphic width that you see right here is the default width of each section. So if I execute the template, and I should have saved my changes, but I'll fix that. Oops. If I go in and say, whenever I drew those graphic widths for each layer, I want it to be 1.5 times larger. And you can see that it made that section much larger. So the whole concept of this formatting is the user is going to create content and you're going to be manipulating this all the time. So we put the preview in there. We allow you to have some flexibility. We allow you to choose the layers that are represented in each section. We allow you to control the spans, the drill spans that are present in each section. And now that I click OK, I have my template, and I'll just go preview so we can get a better visualization of it. Now, I want you to notice that we have cover layers in the right spots. Notice these here. These are core representations. Okay, I can see the cores. I can now, using that core property, which I didn't have before, I can have a unique presentation for cores, even if it's just a standard rigid design. And what I mean by that, I'll go back here. So you remember I set specific cores presentation. So I'm going to just go over here and click on this. And I have this generic core layer stack up. It's just something to show you the concept. I put this down, and now what I want you to pick up on is that the cores, because they're core layers, we understand dielectric prepreg, we understand dielectric cores. Because they're there, I can show cores and dielectrics and prepregs with unique graphics that I can control. So really, it gives you a lot more flexibility with these templates now. Now, some of you who are doing rigid flex design understand that at times, you may need to show the fact that there's an inset. There's a bikini cover layer, so you need to show an inset. So what you can do over here, oh, sorry. Been a while since I've demonstrated. Well, I want to just show you something in the data manager for a second, real quick. Layers. All of the data that we took in, you can now see that the stackups are represented here. So the layers table of blueprint's been updated to support the ability to take all of this layer types and put them into the layer table and present them properly. So I'm going to go back into Stackup Visualizer. And what I'm going to do here is I'm going to go to the properties list and I'm going to add an inset layer, inset column. And what inset is, it represents the amount of intrusion that a cover layer may need to go into a rigid section. So down here where I have my flex core, right? I need these layers to intrude, the cover layers to intrude a bit. So I'm just going to set this. Sorry. Oh, because I'm sorry. I have to choose the flex stack up, or it won't let me edit, which makes sense, doesn't it? So I'm just going to put in a number here, which represents the intrusion of the layers for the inset. Now, inset is a term that we took from the specs. Now, because I made a change to the layer table, it's prompting me, hey, you got to update all these templates. Yes, I do. And you can see now that you actually have the insets showing up in your stackup. So it's a common requirement to show insets in the stackup. A couple other templates that we added. Obviously, we've had 3D stackups before. You can also have a 3D rigid flex stackup. If I want, I don't like that presentation, I can edit it, I can rotate it. Okay. Now, eventually what we're going to do is support the ability to say, I want this 3D stack up to look exactly like this. That piece is not quite here yet. We've also added, as I mentioned, a couple of other templates. We also have a PCB Materials Table. This is something where I want to tell the fabricator, just like you have a parts list for a design with all the component parts and the properties, I want to be able to say, this is a materials list. To build this design, you need a core, you need several cores, you need some dielectric, you need some adhesive, some silkscreen. So it builds a table for the manufacturer of the type of materials they need and the quantities. So this is kind of new to us. If you are doing this kind of thing with your fabricator, we'd love to hear from you. What that gave us, what we did to meet that requirement was we went into and added a whole new table called layer materials. So this can be used for a lot of things, not only just the table. So you can use this in a lot of different templates now. So this is, we gather the materials, we gather the quantities and so forth. So that gives you a little bit more power to use in some of the templates that you might be using on your design. And then finally, you can't have, if I go to assembly drawing now, I'm going to add an assembly drawing. And I'm going to put down a topside view for an assembly drawing. Now, this is the fully assembled built board with all of its board outline, not its layer profiles. But again, I can go in and say, okay, I want to show a layout of just the top layer, right? So I select all these layers. Now I want to show only the signal layer. I'm going to sort of step through this as I go. Now I did that, but I'm still seeing the board outline. I'm not seeing what's only on layer one. I'm still seeing the components that are on inner layers. Let's go back and try to fix that. So I'm going to turn on the layer profile for signal layer one. And for the components, I'm going to sort by these new columns. I don't want to show the parts on the inner layers. So I sort so only the parts come to layer one. Again, I turn off these layers, all these layers, and I turn on only the part on layer one. Preview. Now, the last thing I do is turn off the board outline. So technically, that's layer one, right? In this 8-layer design, that's the top layer. It's that shape using the layer profile. It has that component on it. And that's how I can do, if I need to, individual assembly views and so forth. Now I'm going to drop down another topside view just for the purpose of demonstration, and also show that we've got the side view has been updated as well. So if I turn the side view on this design, you can see, let's try to zoom in here. All the parts are shown in this particular design. See the different thicknesses of the layers. And you can see that the parts are actually appearing on the layers that they're actually mounted on. So even when, as far as updating the side view. And then, of course, you can also add another 3D PCB view. So here's the 3D of a rigid flex sitting on my drawing. Again, I can go in here, edit the 3D view. I can rotate it to whatever position I want for the purpose of my drawing, then go back to the drawing, and it's updated. So, I mean, we've always had 3D PCB view. My point here is that it can actually show the 3D design. So here you see all of the features that I wanted to demonstrate with rigid flex and rigid flex for both CAM350 and blueprint documentation features. And what I'd like to do is I'd like to hand it back to Ray, and we'll start answering some of your questions.
All right, thank you, Mark. You mentioned DFF on the CAM350 side, and you said that there were some new checks planned for rigid flex and flex. Are there any new features in the CAM350 DFF now?
Yeah, so what we did for CAM350, if I had more time, we should have made this an hour and a half. I could talk about this forever. So a couple of things that we've done. For drill and mill checking, we've greatly expanded the drill checking. Before it used to just be, check all drills by this one minimized spacing. Now we can actually do drill to drill types. This is quite an improvement over the previous drill checking. So, especially when you get into these advanced designs where you have different via types, you have laser, you have blind, you have buried. So we really went to town on the drill checking for DFM, and this will be part of the release. And one thing to keep in mind is, I'm just going back to Blueprint for a second, just to illustrate something. So in the rigid flex world, right, think about this for a minute. This is a through via, but so is this. That's a through via, isn't it? Sure it is, because it goes from top to bottom of that stack up. This is a through via, but this is we know that to be a buried via, and this to be a buried via. So it's a buried via here, but it's a through via here. So a big part of the update for CAM350 for this release is to support that. So if you have these advanced vias and you have a rigid flex design, you're going to see initially in this release a lot of better, at least drill checking. We've also added new via and pad checks. So if you have, for instance, vias sitting under a BGA pad, partial vias, through vias under a BGA pad, we allow you now to turn off those checks. I do have vias and pads, don't check them. I do have through vias and pads, don't check. Don't give me all these false errors. So those are the changes that we made for this release. And there'll be, again, I'll go back to Blueprint. If there's a surface mount BGA sitting right here and there's a pad right there, this check is going to be cognizant that, okay, we understand that that's a surface mount pad on layer 4. So it was quite a bit of update we had to do to make sure that all this worked. Good question.
Another question, and I have a follow-up to it. Does it support ODB++ out of Altium? And can you go over, this is myself, can you go over which outputs are supported and to what level for the rigid and rigid flex?
So specifically ODB++. It has been our experience through this process that ODB++ out of Expedition is the most robust ODB++ that we've received to date. So what do I mean by that? If you do the proper design definition in Expedition, give you proper cover layers, give the proper stack ups, when you pass that through ODB, it gives us really robust data that we can properly represent it. A good example is during the development of this tool, we realized that even though the ODB spec had proper definitions to define cores, to our experience, no CAD tool on the planet was writing ODB in that format. Well, Mentor stepped up and they said, oh, we're going to fix that. So if you take your design from Expedition, bring it into Valor and output ODB, you will get core definitions, but otherwise you won't. So that's just an example. 2581 out of Cadence is pretty strong. They are passing the proper areas, but just recall, they are two different format specifications. So there'll be some things that you'll get from ODB, like areas, and some that you won't get from 2581 because the spec doesn't include them as of yet. Now, I know there's a Rev C coming out from the IPC consortium, and there's more proper support for rigid flex in that platform, and we will support it. Today, Cadence is writing what we call IBC 2581B plus. So they are writing sort of a B formatted file with C data in it. And we do accept that because we're testing to it. So we'll probably be, if you will, C ready by the end of the year. But of course, should the consortium make a change between now and its spec release, we'll have to catch up. As far as the original question, Altium, so we've tested a few. I will be honest with you, Altium does not necessarily always follow the spec to the letter. So there are some problems, and so the same is for Zukin. So we have to take them on individual case basis. You send us the file, we'll look at it. I would love to say that Altium files come in, work flawlessly every time, but there's always seems to be some quirky little thing with the files when it comes to rigid flex. So we've have a few that we've tested and validated and worked with, but we need more. If you have some and you can send them to us for testing, please do. We'd accept all formats. The more we test, the better quality import we'll have.
Okay, and a follow-up to that. You showed or talked about how you could create the stackups and stackup zones over on the CAM350 side. Is CAM350 required, or if you're just trying to document this, can all of this be done in Blueprint?
That's correct. If you get the proper file format, you don't need CAM350 as a preempt to Blueprint. That's correct. If the data comes in correctly, right? So just so you understand our 3D visualization, go to CAM350 here. In order for us to understand, I'm showing 3D in CAM350, it's the same in Blueprint. We need to understand where the layers are present and not present. And the only thing that our tools use is that stackup zone. So if you get data and the proper stackup zone's not there, and the proper stackup definitions aren't there, you're not going to be able to visualize it in 3D. And there may be some other drawing issues you face. But if all you have to do is show stackups in Blueprint, as long as the stackups are there, you should be good to go. It's just that your 3D presentation, yeah, if it's not quite properly defined, might be a little awkward looking. But hey, good thing you got that stuff in CAM350 if you really do need to get down to that level. I'm just trying to sell CAM350 licenses.
You know, I'm looking at the users here. Almost all of them have both. So thank you to all of our users that are here that do have both. That is it for the questions.
Okay.
I want to thank you, Mark. Is there anything else you want to add?
No, I think I've covered it all. I will say that if you have rigid flex design data that you're willing to share with us for do our final leg of the testing of this release, we would be very welcome. And if we need to sign NDAs, you know, we have a lot of NDAs with a lot of our customers. The more testing data we have, the better we can be on initial release. We have several examples that we've gotten from many customers, but it always seems that, you know, there's that one file out there that trips us up. So if you have rigid flex data that you'd love to share with us in 2581, ODB, or even pads, I would love to take some pad stuff, Altium, and you're willing to share it with us, please reach out. We'd be very appreciative.
Okay. I want to thank everybody for your time and attending today.